Here are solutions to homework set number 8 for ECE 376. This homework set looks at timer 2 interrupts. Now the first problem is when I build a watering system or timer. Here's what it's supposed to do. When I hit RB0, time is initialized to 5 seconds. It decrements to 0 every millisecond, stopping at 0. When RB1 starts at 10 seconds, decrements down to 0, 15, 20. So how do we do that? Well, in this case, I'm going to use timer 2 interrupts. Here's the interrupt service routine. I'll first set up timer 2 for 1 millisecond. And to get to 1 millisecond, get my pens back, I want A times B times C to be 10,000. That gives you 1 millisecond when running at 10 megahertz with a PIC processor. A is in T2con and C is also in T2con. So if I have 10 times 250 times 4, that gives me 10,000. To get 10, that would be 2ton to be 0, 1, 0, 0, 1. This is A. The way the PIC is set up, each number is offset by 1. That avoids 0. So 9 means 10. That's an enable bit. And 1, 0 means 4. So separating that into nibbles, this is 4D, 12. So there's T2con. PR2 is 249. 249 means 250. Inside the interrupt, I'm going to toggle port A pin 1 just so I can get a square wave out and measure the frequency. I'll then check the push buttons. If I hit RB0, initialize the time to 5,000, 10, 15, 20. That's 5, 10, 15, 20 seconds. And if time is not equal to 0, decrement it. If it is equal to 0, check the buttons. So this checks on the rising edge. Then in the main routine, all the main routine does is just display the current time. And here's what that looks like. You can notice on the rising edge, when I hit the button, time is initialized. As I hold the button down, it's decrementing, because once this is non-zero, it keeps decrementing until I get to 0. Once it gets to 0, I'll check the button again. If I keep hitting the buttons, nothing happens because it ignores the buttons until I get to 0. Once I get to 0, it will check the buttons again. And kind of a subtlety, I can actually have the buttons check on the rising edge or falling edge. This would be the rising edge. When I hit the button, I change time, and then it decrements. This would be the falling edge. When I hold the button down, it's constantly resetting time. It doesn't actually decrement or stop resetting time until I release the button. So that is problem number 1. Problem 2 is looking at building a 1-key piano. So if I want to generate a frequency like 73.42 hertz, what I do is I generate how many clocks between interrupts. N is 10 million divided by 2 times frequency. I want to interrupt toggle every 68,101 clocks. Now that's bigger than the biggest you can do with timer 2. The biggest this can be is 65,536. But I don't have to toggle every interrupt. If I say toggle every second interrupt, that essentially makes that divide by 2, have A times B times C to be 34,000. And one combination that does that is 14 times 152 times 16, gives me 34,048, only off by 2. To do that, A is 13, so this is 13. 1101 is 13, plus 1 means 14. 11 means 16, so this is T2con. Splitting it up into nibbles, this is 6F. So I'll make T2con equal to 6F. And inside the interrupt service routine, I will then count mod 2. Every other count, I toggle. And if I connect port A pin 1 to a frequency counter, that tells me I'm outputting 73.45 Hertz. That's one of the beauties of timer 2 interrupts, is it used to be with C coding, it's kind of hard getting the frequency exact. Here, if I can get A times B times C dead on, the frequency is dead on, 73.45 Hertz. Next problem is a reflex timer. So here's what I wanted to do. When I hit RB0, it starts the timer. Light's going to turn on. That tells me that I am waiting between 3 and 7 seconds. 3 to 7 seconds later, the lights turn on port A. As soon as they turn on, I hit RB0, and it measures the time delay between when the lights turn on and when I push the button, accurate to 0.1 millisecond. So let's start it. So here, I'm going to start it. I'm going to wait for the lights to turn on. 1001, 1002, 1003. So that was 3 seconds later. It was actually 3.4840 seconds. If I want to do better, that was 0.2244 seconds. We're going again. 0.2094 seconds. Now when you write this code, I want to be able to check to see if it works. What I would do initially is just display the time continuously, and that'll sit there and verify that timer 2 is running in the background, is keeping track of time. Once that works, I can then record the time before I hit the button, or when the lights turn on, record the time when I hit the button. The difference in time is my reflex time. So here's kind of the flow chart. When you have interrupts, you're kind of stuck using 2 parallel flow charts because the interrupt could happen at any time. Timer 2 is going to kick in every 0.1 millisecond or 100 microseconds. Every time it interrupts, it just counts. The main routine then, on reset, it waits for me to hit the button. Once I hit the button, it waits between 3 and 7 seconds, then turns on the lights and clears the time. I then wait until I hit RB0. Once I press it, record the time, display it. That's my reflex time. Then repeat. Corresponding code would look like this. Here's the interrupt service routine. I'm going to toggle port CPIN 0. What that does is I can check the frequency. So here's the frequency. It's 500.2 Hertz. No, 5 kilohertz, 5002 Hertz. That's basically telling me that timer 2 is running every 0.1 millisecond, giving 5 kilohertz output. That's what RC0 does. And I increment time. In the main loop, I set up timer 2 for 0.1 millisecond. So A times B times C is 1000. And I did that as A is 1, B is 250, C is 4, giving me this bit pattern. 1 means A is equal to 0. There's my enable bit. C is 0, 1. So that's T2 con. It's going to be 0, 5. And 249 means 250. Enable, 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 enable. And the main routine. I then sit there and wait for you to hit the button. Once I hit the button, I'm going to turn on RE0. That just tells me that the counter is working. Let's slide this over. So the light turns on. 3 to 7 seconds later, the lights turn on port A. I turn on the lights, clear the time, wait for me to hit RB0. When I hit it, save time. That's the time between when the lights turned on and I hit the button. And that turned out to be 4.8473 seconds in this case. And repeat. Next go around, 3 to 7 seconds later, the lights turn on. 0.4471 seconds. Okay, so that's problem 4 and 5. Problem 4. Problem 5 is now collect data. So I recorded my reflex time Monday afternoon. Got 5 times. With that, I can do some statistics. With the 5 data points, I've got a mean, standard deviation. From StatTrack, if I want to have 5% tails with 4 degrees of freedom, meaning sample size of 5, I need to go left and right, 2.13 standard deviations. So that's my reaction time. Here's the mean. I need to go left, 2.13 standard deviations, and need to go right 2.13 standard deviations. And that captures 90% of the area, or 5% tails. Right tail is 5%, left tail is 5%. That says 90% of the time, my reaction time will be between 171 and 202 milliseconds. The probability that my next reaction time will be less than 200 milliseconds. Again, you got this bell-shaped curve. The average is 187 milliseconds. Here's 200. The area is bigger than half. To do that, I find the t-score. That's the distance 200 is from the mean in terms of standard deviations. The t-score is 1.75. To convert 1.75 to a probability, I need to use a t-table. Now my sample size was 5, meaning 4 degrees of freedom. So I come over here at 4 degrees of freedom, look for the number 1.75, and that's right around here. Maybe about 12%. So the tail has an area of 12%. The left side is an area of 88%. 1.75. Nope, I did that wrong. It's about between 0.5% and 10%, say 8%. So this has an area of 8%, making this 92%. So 92% chance my reaction time will be less than 200 milliseconds. My population, say, what's my average reaction time? That's a population question. For populations, you divide by the square root of the sample size. So I'm now 3.93 standard deviations out. Going back to the t-table, look for the number 3.93, and that's in here. It's between 0.5% and 1%. Say about 0.9%. So about 9.1% chance that my average reaction time is less than 200 milliseconds. 0.9% chance it's more. So that's the t-test with a single population. If you want to compare populations, what I could do is change something. Like the first sample was measured in the afternoon. This is early morning, my reaction time. Is there a difference? Well, to tell, I take the second set of data. Each set of data has a mean, standard deviation. Form a new variable w. That's the difference in the two. The mean of w is just the mean of A minus mean of B. So on average, in the afternoon, I'm 11 milliseconds slower than in the morning. Has a standard deviation. So again, w is a bell-shaped curve. The mean is 11.3 milliseconds. Standard deviation 12 milliseconds. To say, is A greater than B? That's this area. It's how far is 11.3 from 0 in terms of standard deviations. That's your t-score. The t-score is x mean minus 0, since I'm going to 0, over the standard deviations. This is 0.8962 standard deviations away. Again, going back to a t-table, look for the number 0.89, and that's right around here, maybe 25%. So 25% chance that A is less than B, 75% chance A is greater than B. Or 75% chance that my reaction time is better in the morning than in the afternoon. That's for single sample. If I want to know overall, do I have better reaction times in the morning than afternoon? That's a population question. For populations, you divide the variance by the sample size, or the standard deviation by the square root of the sample size. Find the new t-score. For the population, I'm 2 deviations out. So again, go to the table, look for 2, and that's between here, between 5% and 10%, closer to 5, say maybe 6%. Meaning 94% chance that my reaction time in the morning is better than afternoon, 6% chance the other way around. So that is homework set number 8, timer 2 interrupts. With timer 2 interrupts, I can generate a precise frequency or record time precisely. And with that, I can start collecting data, like reaction times or other things like that. That's homework set number 8 for ECE 376.